Um, Good morning, my YouTube viewers. It's Crystal here. I'm just here because I wanted to do a code review with you. I wanted to go over a recent Kaggle competition and just to give you my take on it. I had no expectations of winning the competition, but I decided just to give it a go yesterday afternoon because I had a little bit of free time. And because I had a little bit of free time, I thought, oh, well, I'll see if there are any Kaggle competitions that I can enter. So I can't enter most of the Kaggle competitions. It's partly because I haven't received the adequate training to do it, and partly because my computer is not powerful enough, and because my computer is not powerful enough, I can't do it. But this was one dealing with natural language processing, and I can do natural language processing, and I've also made a course on Udemy with regard to natural language processing as well. And if you're interested in the course, please let me know. I'll see if I can get a link for you to take the course if that's something that you would like to do. And so this is a competition that involves natural language processing, and it is in the Kaggle website, and if you go into competitions, then you will find it. And so I just put a really short problem statement. I did a public score of 0.54, where the best score was 0.43. I got a bronze medal for this. I certainly never expected to get any bronze medal, but apparently they felt that I presented some good code, so they gave me a bronze medal, even though I certainly didn't win. The problem statement for this competition question is, the goal of this competition is to assess the language proficiency of 8th to 12th grade English language learners. Utilizing a dataset of essays written by ELLs will help to develop proficiency models that better support all students. So that's just a very small problem statement. But if you go onto the Kaggle website and you check this particular competition, then it will give you more information where it's just said you're supposed to use natural language processing and analytics. So after we created the program in Kaggle's Jupyter Notebook, because in all of the Kaggle competitions that I enter, I create the program in their Jupyter Notebook because it's free. Excuse me, you don't have to pay anything for it. So after I created this program, I imported my libraries. So I imported NumPy as NP, which is the numerical computation library, and it also creates NumPy arrays. I imported Pandas as PD, which creates and manipulates data frames, and it does data processing. I imported OS because it goes into the operating system and retrieves the files that we're going to use to run the program. I imported matplotlib.pyplot as PLT because it is a graphics library that plots the data points onto a graph. I imported Seaborn as SNS, which is a higher level graphics library written on top of matplotlib. After I've imported my libraries, I loaded the files, and so I use this piece of code here to load the files, and this piece of code here is actually in the Kaggle Jupyter Notebook, so it helps you to actually get the files. And so we had 3 files: train, test, and sample submission. After I loaded the files up, I read the files. So I created the data frame train for the train file. I created the data frame test for the test file, and I created the data frame submission for the sample submission file. So here you can see the train file here. You have a text ID, a full text, and then you have 6 outputs. So cohesion, syntax, vocabulary, phraseology, grammar, and conventions. So you have 6 outputs that you have to make predictions for, and only 1 column of text. So we look at the test file. The test file has only 3 pieces of text, and it doesn't have an output. So what we have to do is we have to predict on the output, which is the y variable. And so we check the submission file. The submission file has 3 rows of data that we have to make prediction on, and it has six outputs of cohesion, syntax, vocabulary, phraseology, grammar, and conventions. So that's what our submission file has to look like. So what I decided to do was I decided to analyze the outputs. So I did his-plot on cohesion, and you can see cohesion, the highest frequency is a 3. We did a his-plot on syntax. The highest frequency is 3. We did a his-plot on vocabulary. The highest frequency is 3. We did a his-plot on phraseology. The highest frequency is 3. We did a his-plot on grammar. The highest frequency is 3 again. And we did a his-plot on conventions, and the highest frequency is 3. So we've done a his-plot on all 3 outputs, and all 3 outputs make like something similar to a Gaussian curve, which is a bell curve. And so now what we're going to do is we're going to define our target. And I called it features, but really it's not features. Features is columns, but I didn't know what to call it, so I just called it features, but it's not features. Feature is generally a column. Well, I guess it is a column. I guess I was right. But features equals cohesion, syntax, vocabulary, phraseology, grammar, and conventions. Target equals train features, and then you print your target, and you can see you got 3911 rows by 6 columns, and your 6 columns is your target. So now what we're going to do is we're going to combine our train and test. So text train equals train full text. Text test equals test full text. Text equals text train dot append text test. And then you can see the text test, so you can see the train and the train text and the text text appended to it. Now we're going to analyze the text. So we're going to count the words, and it's 1,707,247 words. Now we're going to process and clean the text. But the problem is whenever you enter a competition with Kaggle, and this was a live competition as well, you have to turn off the internet. And so basically what you have to do is when you turn off the internet, then you're only able to use the libraries that are actually in loaded into Kaggle. So it looks to me like NLTK is not actually loaded into Kaggle. I don't know why that is, but NLTK does not work when you turn off the internet. And I'm just working on the assumption that it's no longer loaded into Kaggle. And since it's no longer loaded into Kaggle, what that means is I was not able to use the bits of code relating specifically to NLTK. And so what that means ultimately is because the internet is turned off, and programmers are only allowed to use the libraries that are actually in Kaggle. What that means is that they have to use more different types of programming. They have to work around their programming in order to actually get the program to work. Like for instance, NLTK does not work when the internet is turned off. And since NLTK does not work when the internet is turned off, I cannot use those pieces of code that deal specifically with NLTK. And so rather than delete them, I just hashed them out just so you can see what I had to hash out to get the code to work. So the library reworked. So we were able to clean the text. Text equals text.string lower. So that means we converted the text all to lowercase. We removed special characters. Text equals text.apply, lambda x, colon, read.sub, and then that just shows you the only characters that are allowed in the text. And then we removed hashtags. Text equals text.string.replace, hashtag with a space. And then we removed words less than 3 characters and greater than 70. And that's another lambda. Text equals text.apply, brackets lambda x, colon, space dot join, brackets, square brackets, w for w in x dot split, brackets, if len w is greater than 2 and len w is less than 8. So that's removing all words less than 3 characters and greater than 7. So we can't remove these stop words, and the reason why is because stop words is part of NLTK, and we can't use NLTK in this program. So we counted the words, and we had 1,065,764. Now I decided what I would do is I would remove the frequently used words. Most underscore freak underscore words equals PD series, because in pandas you can make a series is just one column of data. Brackets space dot join, brackets text dot lower, brackets dot split, brackets dot value counts, brackets 25. So it's just removing the 25 most frequently used words. Text equals text dot apply, brackets lambda x colon space dot join, brackets word for word in x split, brackets if word not in most freq words. Print most freq words, and then you count it. So we took out the 25 most frequently used words, and we could have taken more because there's not any stop words, and since there's not any stop words, you could have taken out more frequently used words, but you've already taken out all the words that are less than 3 and greater than 7. And then now you have 661,706 words to analyze. Now we have our Apostrophe Dictionary, and what the Apostrophe Dictionary is a dictionary that takes the apostrophized words and it converts them to what they would be without apostrophes. So you can see all that. So now what we do is we put in a function to replace words in the dictionary. So def lookup underscore dict, brackets, text, comma, dictionary. For word in text dot split, brackets, colon, if word dot lower, brackets in dictionary, colon, if word dot lower, brackets in text dot split, brackets, colon, text equals text dot replace, brackets, word, dictionary, square brackets, word dot lower, brackets, square brackets, brackets, return text. And so we're going to implement this function. Text equals text dot apply, brackets lambda x colon look up dict, brackets, X, comma, apostrophe dict, brackets. So now what that does is that takes all of the words that were apostrophized and it converts them to what they would be if they were not apostrophized. Now what we're going to do is we're going to remove the rare words. And rare words is like if you have only one word, then it's going to remove all of them. So from all of those words there's only one count. From collections, import counter. From iter tools, import chain. And then we're going to split the word into list. V equals text dot string dot split brackets dot to list brackets. And we're going to compute global word frequency. C equals counter brackets chain dot from iterable brackets V brackets. Now we're going to filter, join, and reassign. So tweets equals square brackets space dot join brackets square brackets J for J and I if C brackets square brackets J square brackets greater than 1 brackets for I and V. So what it will do, which I did actually make a mistake in that because it said tweets and it should have said words. So I think that whenever I finish this code review, I'm going to take the tweets and convert it to text because that I'm surprised because it didn't work. It didn't take out the rare words because of that. So I'll try it again and see if that improves my score. So just right here, it shouldn't be tweets. It should be text. And then that's something that I missed, which it's always a good idea to do these code reviews because then you can go through the code and if you've made a mistake, you can pick that mistake out. So 667,552. Let's see what we've got here. So, but now you just got 667,552 words. So now what we're going to do is we're going to find X, Y, and X test. Y equals your target. X equals text, square brackets, colon, len train, square brackets. X test equals text, square brackets, len train to colon. And then we check out X shape, X test shape, and Y shape. So you can see X and X test are 3 columns. Are 0 or 1 column, whereas Y shape is 6 columns. So we're going to convert text frequency. And this is another thing that I had problems with because I could not use train test split. The reason why I could not use train test split is because in one of the categories in the output or the target, there was only one of them. And if there's only one of them, then train test split won't work. And I suppose that if I had really wanted to, I could have used another method to split it up. But I decided in this instance just to not use train test split and just use the X and the Y values, X test and Y values in that. So from sklearn.featureextraction.text, import TF-IDF vectorizer. TF-IDF vectorizer equals TF-IDF vectorizer brackets stop words equals English, comma, max DF equals 0.5, comma, min DF equals 0.01. And what that means is in this in this function with sklearn, it has its own stop words in it. So we can't use xtrain because normally we would use xtrain and xcal. We can't use that in this instance because we didn't use train test split. So x equals x dot to list brackets, x equals list brackets map brackets space dot join comma x brackets. And then we use xtest, and xtest is xtest equals np dot array brackets xtest dot to list brackets xtest equals list map brackets space dot join comma xtest brackets. And now we put the data into the TF-IDF vectorizer. So x underscore TF-IDF equals vectorizer TF-IDF dot fit transform x. X test underscore TF-IDF equals vectorizer underscore TF-IDF dot transform x test. And then we print vectorizer TF-IDF dot get feature names out is 5. And then so you get the first 5 feature names, it's going to print it out. So we check the shape of x TF-IDF, x test TF-IDF, and y, and that's 3911 for 892 columns, 3 rows with 892 columns, and the y is 3911 of 6 columns because that's your output. So now what we do is we check our output, and in this instance we're using a multi-output regressor, and because the model would not accept a multi-output classifier, and because the model would not accept a multi-output classifier, we had to use a multi-output regressor because it's saying that it was continuous. And I had thought about label encoding the output, but if I had label encoded the output, then the numbers would not be the same as what the numbers were in the actual output. So I decided against that. So from sklearn.multi-output, import multi-output regressor. From sklearn.svm, import SVR, that's your support vector regressor. Chain equals multi-output regressor, SVR, brackets, brackets. Chain fit equals X TF-IDF Y, print chain score X TF-IDF Y, and that's a 86.5% accuracy. And what I had previously done was I had done multi-chain regressor, and I used multi-chain regressor, and one thing that I found out is it didn't affect the output. It didn't affect the score whether I used multi-output regressor or chain regressor, but I had a higher accuracy with multi-output regressor than I did with chain regressor. So now what we're going to do is we're going to predict on X test. Predictions equals chain dot predict X test TF-IDF, and these are your predictions. So you've got 3 rows of data with 6 predictions. And this is your sample submission, and then so your submission has 6 columns. So the cohesion is column 0, syntax is column 1, vocabulary is column 2, phraseology is column 3, grammar is column 4, and conventions is column 5. And then I prepared this to be submitted to Kaggle. Submission.toCSV equals submission, comma, index equals false, submission equals pdread CSV, submission.csv, submission. So you can see this is our submission. And the thing is about the submission that all of the values range between 2 and 3, or range between values of 2 and 3. So that is the code review, and I did actually find a mistake, and so when I finish this code review I'm going to go through and change the mistake and see if that improves my score, because that's what it's all about is improving your score. I've got a score of 0.54, but the best score was 0.43. But if I go through and change that one mistake that I made, that I brought that to your attention, then maybe there's a possibility my score will improve, even if it made it 0.53, that would be fantastic, wouldn't it? So I'm going to go ahead and close this video because I've been speaking almost half an hour to go over the code with you. So would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. Thank you very much for watching this video, and I look forward to making more code reviews for you in the future.